Got it. Right, okay. Okay, look at that. This is the file that our tool reported. Okay, so added into the gateway probe, just a little thing which writes out to a CVS file. Okay, so we've got that in these functions here. Okay, this is on the repo, so don't worry. Okay, that file is what we recorded, even down to the success at the end. This, on this file, on this side, is what the server recorded. The exact same events in different formats. Okay, the target did not need our recording of that to know what happened. It kept its own record. And what we're doing this week is we're building on the tool, or we're building a tool that reads records like ours, okay, and raises an alert. Okay, so on we go. Chapter 1. Okay, so from our perspective, the tool works, okay? In terms of an actual session, it passed the thing, it found the password. Okay, so that was session A. This week, I think we've got one quite important question to ask, is that given that log of data, either your tool or the one produced by the target in the auth log, can we write a program that reads it and automatically identifies an attack pattern? Okay, and that's what we're trying to do here with this. And to do that, we're going to write detect probe. Okay, so before building it, we need to understand something about the two log formats, okay, that have just appeared on the screen because they're telling the story, but in two completely different languages. 1 second. Okay, so let's view the real authentication log. Okay, this is our file that we've got there, but this is exactly what, and it's still waiting and it's still listening now. This is what the server is catching. Okay, so this is our log of usernames and passwords that we've attempted to capture which one it is that worked. Okay, and this is the system log, which gives us everything that's happened on there, okay, including the successful login. Successful, as we can see there, that was the last login. So because this is in essence, the actual full log for the system, okay, it doesn't just include our attack attempts, okay, it will include every password authentication management event on the machine, not just FTP, not just SSH, anything that can authenticate. Okay, so filtering into events like that actually matters a lot because there's an awful lot of detail there. So what we've got here in our attempts.csv file, okay, are the same events, okay, absolutely the same, except look at the format, okay. So this is in essence syslog. If you look at the timestamp, let me see if I can zoom in a little bit. Okay, look at the timestamp there. All right, that timestamp doesn't have a year. Okay, um, it doesn't necessarily have a host name. It has a service name with a process identifier in brackets. The password authentication management subsystem is the one that provides the event detail. Often processes such as ProFTPD can pass their output straight into the authentication system. Look at this one now. Let's move in again on this. Look at our timestamp. Okay, we've got everything captured in this file using ISO 8601 timestamps. We've got the password result, we've got the username, okay, and we've got the source IP address. One row per event, deliberately machine readable. Okay, now don't forget, this is what we produced. This is what the server produced. Okay, and as I've said, they describe the same events. Okay, but but this reflects how logging actually works across real systems. This isn't the first time we've had to adjust and write timestamps. And in fact, in order to successfully pull this one through, okay, I had to update and add a regular expression for ProFTPD, but also because of the different timestamps we're dealing with, okay, depending on whether we're coming out of an SSH log or whether we're coming out of a syslog timestamp, we've had to add those things in there. Okay, so our detect probe file, okay, is built to work against, okay, our attempts.csv file. That's what we're working with here. Okay, and that structured output is a good starting point. But hopefully, by the end of this session, okay, we should be able to take out all of that information, okay, and produce back a tool that gives us a report and an alert. All right, okay, so the file in this file is the attacker's record in essence. Hundreds and hundreds and hundreds of attempts, yeah, and one success, right? All in all, that's not a lot of time for those to take place, and you saw that happened. Now, consider what a security analyst sees when they find the equivalent record, whether it's in attempt CSV or in the filtered output from the auth log. Okay, they see a pattern: authentication events in a short period of time followed by a success. Okay, a single source, a single target account with the last attempt succeeding. So the only thing that they can conclude is that it's automated. Nobody types that many passwords in that many seconds. It's not a user who forgot their password, because a user forgot their password does not try 6 systematically different credentials in rapid succession. Okay, they would type passwords that are similar. Successful, the attacker now has a valid credential. Okay, this is drawn from the pattern. We can see it in the logs. Too many failures, too short a time window, too regular an interval between the attacks. Okay, so let's have a look at detect.probe and see what it does. Right, okay. So this is a pure log analysis program. In a way, we're looping back to where we were with our gateway parser in week 1, but we're looking at this and the gateway probe, if you like, we're looking at this from a blue team's perspective. Okay, so we're sat inside the blue team's chair. Okay, so what we've got to think about are the two detection patterns that we're looking at. Okay, so this is a guessing detection in a way, because the the attacker has targeted one account. They've tried one password after another, all from the same source IP address. Okay, and that gives us information about too many authentication failures against a single account. Okay, so the key here we're looking at is user and source. Okay, so that's the user account and where the attack came from in essence. Okay, the other thing we can look at is spraying detection, and we talked about the different kinds of attacks last session. Yeah, so this is a different strategy where an attacker can try one common password against every account on the system. So that's one attempt per account distributed across users. It's a different signal. It's a different piece of information that's coming back for us. Failures distributed across multiple distinct counts, all from assistance, all from a single source within a short time window. So the key that we need to look for there is the source address of where the attack came from and count distinct failed users within a time window. Okay, if the count exceeds the threshold, then we produce an alert. Okay, so both patterns are present in the same data format. The difference is only a question of which way are we going to look for it and what decisions are we going to make. Okay, if the same tool iterated users instead of passwords, typing in password 1 against Vagrant, and then against another account, and then against root, that's spraying. Okay, so we need to think about how we can capture this onto us. Right. Right, okay. So, chapter 5, detect probe itself. Let's have a look. Right, so we've seen this pattern before. It's one that we're all familiar with. Okay, same design principles, 4 functions. Each function has one job. Okay, load attempts, reads the files and handles all of the parsing, including timestamp conversions from the strings to a date time format. Okay, that's a Python datetime object, does nothing else. Okay, the detection function receives the records. It doesn't really care about any of the file formats. Main's the one that coordinates all that lot. Okay. And this is a good design principle, again, in the sense that if the timestamp format in the attempts.csv file changes, then load attempts is the only function that needs to change. Okay, the detection algorithm doesn't need to change. If a new detection pattern is needed, then a new function is needed alongside the existing two. Okay, so again, main doesn't change. Each function has its own reason to do that. Okay, right. So let's talk a little bit about the sliding window. Okay, so a sliding window, that's something that you should be familiar with from things like sliding window from networking. Okay, we can see that it's a detection algorithm. Okay, in this context, I think it's worthwhile getting our head around this concept because in essence we're going to be programming this. So a sliding window is a bounded time interval, okay, that we can see there, and it moves through a sequence of time-stamped events. For each event, the window looks backwards by a fixed duration. 60 seconds is usually the default, and therefore for that event, count how many prior events fall within the backward looking window. So if that count or meets an extent, if that count meets or exceeds a threshold, okay, then we raise an alert on that one. Okay, right. So back into VS Code now. Let's just create a new file. Okay, and I'm just going to call it window.py. If I can type, that is window.py. Okay, and in this instance, I'm just going to simulate that flow. Okay, so let's run that and see where we go with it. Let me best save it first, hadn't I? So Python 3, window.py. Okay, right. Okay, there we go. So in this instance, okay, the data was dummy, but it gets the point. Okay, so the fifth event in this list crossed a threshold. Okay, and we decided what that threshold was down here. Okay, we've got a count event there, look. Okay, and we'll talk more about that in a bit. Yeah, so file failures within a 60-second window of the fifth event's timestamps. The later events, okay, what is in essence at 9:05, etc., they don't count. Okay, only 2 events precede them with their own 60-second window. The window slides, okay, it's not fixed in any way, shape, or form. Okay, it's not fixed in any way, shape, or form. Okay, the window anchors to the event and then looks backwards. Okay, so that means if an attack that straddles the clock by a minute boundary, it's still detected. Okay, the detection does not depend on when the clock sits. Okay, so in our detect guessing here, this is the logic that we'll apply for. Okay, so we'll use a source group to look for that, and we'll apply that to a subset of the data so that only the events that target a specific account from that specific resource. Okay, that's the detect guessing. Right, okay. Okay, so chapter 8, the core detection code. Okay, right. So let's get rolling a little bit more, shall we? Right. So let's just expand that out again. Okay, and we shall pop in our imports first. Okay, let's get those in there. Okay, right. So again, we're just dealing with some date time and some time delta classes, okay, which gives us a difference between two date time values. Okay, we've got our collections module, okay, and that looks at various different data types. And in this one, we can bring in a default dictionary class, okay. Then we've got pathlib, which we're familiar with, CSV for reading CSV files, argparse, and sys for our error stuff. Right, okay, so now let's look at load attempts. Okay, let's just pop that one in there. Okay, so a quick run through that. We're passing in a path as a string, and we're going to return a list of dictionaries. Okay, so we're checking the path exists, and if it doesn't, and again, we're opening the path using the with keyword as our file handler F. Okay, and in this case, we've got csv.dictReader. Okay, so this reads the file and maps each row to a dictionary using the header using the header row as the keys. So the timestamp field in each dictionary is still a string at this point. Yeah, date time dot from is from ISO format converts it to the date time object that we need. Okay, the filter at the end, okay, where we're building that up in the list comprehension. Okay, so the filter that we've got there at end removes any rows that say success. Okay, detection is only concerned with failures. A succession of failures followed by a succession in the signature. The failures are the signal, the success is the outcome. Okay, so our detect probe program here doesn't alert on that. Okay, it only alerts if the pattern of failures precedes it. Okay, now let's move on to detect guessing. Okay, so detect guessing. Right, okay, so again, let's look through the file. Okay, so we've got a list of alerts. Okay, but this here, default dict list, a dictionary where accessing a missing key automatically creates an empty list. Okay, the grouping loop adds each attempt record to the list for its user and source. Okay, and that's the elements that we're looking after. Okay, after the loop, each key maps to all failure events for that user and that source combination. So for each group, records are sorted by timestamp, and then for each event, okay, each event, the window looks back 60 seconds. Everything in that window is counted. If the count meets a certain threshold, an alert dictionary is appended and the inner loop breaks. Okay, and this break line matters because without it, the function emits an alert for every event after the threshold if first crossed within a group. Okay, that becomes alert noise, and sysadmins will switch off from that. Okay, we fire the alert at the first moment the threshold is crossed. Okay, and that's the best way to do that because that's what a real detection system would trigger. Okay, let's look at the other approach now of spraying. Okay, so this time we're looking at a different kind of key that we're going to aggregate our data on. Okay, and I'll tidy this up and I'll add comments and push that up to the repo afterwards so you can see it. Okay, so in essence, the structure that we're using here is absolutely identical to the detect guessing function that we've just written. Okay, it's just that the aggregation key has changed from user source, okay, to just the source on itself. Okay, so one line changes the entirety of the logic. Okay, okay, our distinct users, okay, is set within that there. Okay, and we use a set again, okay, because a set will discard duplicates. Okay, so if the window contains 10 failures against a particular user account and 5 against another and 3 against root, say for example, all right, the set has 3 elements, 3 distinct users. If the threshold is 3, that is what triggers. So a guessing attacker tries many passwords against one account. A spraying attacker tries one password against many accounts. Okay, guessing gives us a high failure rate, where spraying gives us that high distinct use account per source. The threshold defaults are different deliberately. Guessing a threshold of 5 is a generous allowance for a user who misremembers their passwords. A spraying threshold of 3, so 3 distinct account failures from one source in 60 seconds, I would suggest that that already feels a little bit off. Okay, a legitimate user doesn't try to log in on 3 different accounts in less than a minute or so. Right, okay. So we've got our main bodies here. All right, let's dive down and have a look at our main one. All right, so let's build in the main. Okay, so let's build up main. I've just dropped the arg parser in here. Ideally, that should be separated out into a separate function as we've done previously, but for now, that's absolutely fine. Okay, and if we look down here, we're building up the logic. So we're going to deal with our parsers. We're going to load in our attempts. Okay, so that's going to be our log file. So in this case, that could be attempt CSV, depending on which one we're going to look at. Okay, and then we're going to go and call in the various different logic. So we're going to detect guessing and we're going to detect spraying. Okay, so we'll see how that one works. And then finally, we've got some output here down in the bottom of the file. Okay, so if it comes up with guessing alerts or it comes up with spraying alerts. I just want us to think about the timestamp as well that we're capturing here. Okay, not the last event. The timestamp in this context is the moment that the threshold was first crossed. So in the examples earlier, that would be the 5th failure. Okay, that's when a detection system in reality, such as snort or fail to ban, would trigger. Okay, not after the attack is completed, but the moment the moment when the pattern became unambiguous from a logging perspective. Okay, now let's have a go and run that from the logs. As is usual, everything could possibly happen. Right, so Python 3, detect, detect probe.py minus minus log. Okay, and in this case, the log file is in the local directory. And we'll just go with access. Oh, it should be in the local directory. Let me just check. Attempts, not access. That's why I wasn't picking it up. There we are. Okay, nothing. Brilliant. Might help if I added some other bits onto it. Let's change that to threshold 3. Okay, there we go. So alert guessing 6 failed attempts for user vagrant from 172.16.19 in 60-second window. Okay, first detected at 12:09. Okay, spraying, there are 5 distinct users targeted. Okay, and that was first detected at 12:56:03. Okay, so we can do a lot of tuning with our element. So we can look at tuning the thresholds, or we can look at tuning the windows. Okay, and these in essence are kind of failure modes for all detection systems. So the first thing really we've got to think about are false positives. So the detector alerts when there's no attack occurring. A user genuinely misremembers their password and tries 3 variants and triggers a guessing alert. Okay, that is if the threshold is set to 3. IT support calls, no attack happened. Okay, if this happens too often, alerts stop meaning anything. Oppositely, a false negative is where attack occurs and no alert fires. Okay, so an attacker who knows the threshold is 5 tries 4 passwords and then waits 2 hours. Yeah, and then tries 4 more. In other words, the detector never actually gets triggered. Okay, if we lower the threshold, you can have more false positives and fewer false negatives. The higher the threshold, fewer false positives, but more false negatives. Okay, there's no setting that eliminates both. Okay, it's something that you're just going to have to fiddle around with and experiment. Okay, the window setting as well that we set inside has same trade-offs, but just looking at a different dimension. If we look inside our gateway probe, if we look inside our gateway probe, okay, we can see it uses time sleep, okay, 10 attempts per second. A 60-second window captures up to 600 attempts from such a tool as this. If the attacker increases the sleep to 5, only 12 fall within 60 seconds. Again, increase the window to 10 minutes, up to 120 attempts. The window and the threshold are always a pair, and understanding that trade-off is what you need to get your head around with this. Okay, right, let's look at something else for a minute. Okay, the two detection patterns here map to documented behaviors in the MITRE attack framework. Okay, so and here we're looking at a framework of IDT1110. Yeah, and there are various different sub techniques. Yeah, so 0, dot dot 1, etc. as you can see there. Okay, so number one is brute force password guessing, exactly what we've just been doing this time round. Okay, and there's plenty of information out on there. Okay, number three is what we've also done on this one, which is password spraying. So a small number of common passwords against many accounts. Okay, and that's what our detect underscore spraying detects. And I've also added in a gateway underscore spray that will actually undertake the spraying attack as well as the probe attack. Okay, so have a look at that. But each of these elements, okay, exist on the MITRE attack framework, and this provides a wealth of information about known and documented attack types across a whole range of different attack vectors. So it's worthwhile having a look at that. Okay, final chapter. Right. Okay, let's run a scan. We can see something's happening there. Let's see what we get back. Part 21. We know that. It's done. The credential is found. Likewise, port 22, we can get into that one. But what about port 80? We've never had an output from port 80. Yeah, we've never sent a single request to it. And some ports, as we know, don't pull back unless we send information to them. Hello, that's interesting. One unauthenticated request. The server responded with its software name, its version, the PHP version running behind it, and the operating system it's hosted on. No credentials, no exploit, just one simple request using well-known tools. Apache 2.4.7 and PHP 5.3.10 are both documented to have known CVEs, and the server just handed that information over to us without being asked. That's not necessarily a vulnerability in the system. Okay, that's the system behaving as it expected to and disclosing information to us. FTP as a process has one real entry point, the login prompt, where the web layer itself has service response headers, HTML source, standard paths. Some of those paths will return 404, some will return 200. The ones that return 200 errors disclose something about the server's configuration that the administrators probably did not intend to expose. However, none of that is visible yet. The one curl command that we've just issued retrieved all 3 lines of version information. Yeah, just think what we could retrieve if we wrote a systematic tool that could pull all of that out. Every header, every path, every comment in the HTML source code, all done within a single run. That tool does not exist yet. That tool is what we'll create in week 4. Right, okay, we're done. Pull this down from the repository. Okay, there's some other files in there for you to look at. There's detect probe that we've done. There's gateway spray that we've got in there. Okay, so you can have a look at that. There's a user list there with different users that you can try. And also there's a poison word list, okay, which will break your code if you haven't handled any of the errors properly.